video will focus on learning how to map electrons using the quantum model, so orbital theory. By the end of this video, you will not be able to do this learning target, but it's the pieces of the puzzle that you will need in order to actually do it in class. So what we're working on here is building kind of a foundation of what the quantum model for the element or for the atom actually looks like. Okay, all I'm giving today are essentially the rules of the game. I'm showing you Schrodinger's equation in terms of the components that came from his equation when it comes to mapping electrons. Okay, it'll kind of talk about the difference between the Bohr model and the quantum model, but essentially all we're doing here is giving you the rules of the game. Get the rules down, and in class we'll apply the game. So the big thing about Schrodinger's equation, he still has energy levels, just like Bohr did. So Bohr's idea of concentric rings still exists in Schrodinger's equation. He has energy levels. But the big change in the Schrodinger's equation is that he doesn't just have energy levels, he also has something called an orbital. And an orbital is a region in space, so a three-dimensional area in space where electrons tend to reside about 95% of the time. So we know the concentric ring thing is not true. That's the part of the Bohr model that went kaput. So it's been replaced by this idea of orbitals, that electrons tend to reside in these regions in space, and they don't move in these circles, they just reside somewhere in these spaces. So to kind of take your Bohr model and bring it up a level, number one, the quantum model does have that principal energy level, as I said. We usually call it N, or the principal quantum number, which that in my brain is like the ring. So the ring is gone, but the model is good to think about. So the Schrodinger model, the quantum model, said there are principal energy levels, and we just call them numbers, 1, 2, 3, 4, 5, 6, 7, and they pretty much correspond to the rows on the periodic table. Okay, and in your brain, you can think of them as the rings. So as we increase our principal quantum number, we go further from the nucleus. Okay, the thing that's new about this model, though, is this orbital idea. So these regions in space where electrons tend to reside, each energy level will have its own orbitals, and some will have multiple orbitals. So we almost call an orbital a sublevel. Okay, we have a sublevel within our energy levels where there are specific orbital shapes. The rest of this video is going to focus on those orbital shapes for you to kind of build what the model looks like. So the first potential sublevel that exists is the sublevel S. And that S sublevel contains the S orbital. That S orbital is just one potential spherical shape, and that spherical shape holds 2 electrons. So on energy level 1, there's an S, and we call it 1s. On energy level 2, there's an S, and we call it 2s. On energy level 3, there's an S, and we call that 3s. And the difference between all of them is just their size. Just like the rings got further and further out, the orbitals get bigger and bigger as you go to a higher energy level. What's similar about all the S's? Always spherical, always 2 electrons. The next potential sublevel in terms of energy would be a p sublevel. It actually has 3 orbitals within its one sublevel. So you can see like one orients around the x-axis, one the y, one the z. Each one of these images here, each one of these pink kind of dumbbell-looking shapes can hold 2 electrons. So the p sublevel holds up to 6 electrons, 2 per orbital. And the p sublevel shows up as of the second ring, as of energy level 2. So on 1, you only have S, 1s, but as of 2, you have 2s as well as 2p. So 2 electrons in S, 6 electrons in p, giving you 8, which is where 8 came from in the first place for the Bohr model. So there's lots of similarities here. The next sublevel from there, you can potentially have a D sublevel. You can see here for D, you have 5 potential orbitals, 5 different orientations. Each orbital, again, holds 2 electrons. That's universal. No matter which orbital we're talking about, they hold 2 electrons. It just depends on how many orientations you have in any given sublevel. So the D sublevel will then hold 10 electrons, and the first D sublevel shows up on energy level 3. So 1 just has S, 1s. 2 has S and P, 2s, 2p. As of 3, you have 3s, 3p, and 3d. So 10 plus 6 plus 2 for a total of 18 electrons as of that energy level. There's one more potential orbital sublevel, and that's F. Okay, F has 7 different orbitals within that sublevel, 2 per orbital, 14 total. That one shows up as of energy level 4. So now we've got the 14 and the 10 and the 6 and the 2 all showing up as a 4. So there's a 4s, a 4p, a 4d, and a 4f. The goal of all of this is that eventually, if I say map all the electrons for copper, we can place every single electron in its energy level in its orbital. So the Schrodinger's equation gives us these factors to find where exactly an electron is. And based on its location, we can determine like how it will react and things like that. This is an image of kind of a summary of all those orbitals. You can see 1s, 3p's, 5d's, 7f's. Each one of these shapes, again, is going to hold 2 electrons, no more than that. And I'm going to leave this one up here for you guys at the end if you want to write this down. This is a nice summary of a lot of the content that I said out loud to you, so it's not a bad chart to have. That's it for this video. Have a nice night.